Hello and welcome back to Calculus 1. This is section 4.1, starting chapter 4 on application of derivatives, and we are going to talk about min and max today. When you take a look, why are you purple? There we go. So when you take a look at, let's say, a function that will look something like this, we can put that in some xy coordinate system. It doesn't really matter. We actually don't need this coordinate system at all. I'm just going to get rid of it. Or leave it. Whatever. We are focusing on these points, and if you take a look carefully, you will see that all of them have what we call horizontal tangency. Horizontal tangency is a tangent line that is horizontal, hence the slope is 0. So whether you have minimum or a maximum, the slope of the tangent line is always 0. So this tells us that we can find the location, right? The x location, which gives us these values. We can find it by simply setting the derivative equal to 0. So it's opposite procedure from what we have when we look for the tangent line. When you look for tangent line, you have a function, you find the derivative, and then you plug in an x to get the slope. Now you know that the slope needs to be 0, so when you take the derivative, you set the derivative equal to 0. So we'll say to find x at which we have min/max, set f prime of x equal to 0, and solve the equation. Now, this is not the end of the story. Otherwise, if that was it, right, the next words would be, all right, 4.2. There's more than this. So let's go and define some terms first. We have to distinguish between what we would call absolute, also known as general, max min, or relative, also known as local max min. Those are not the same. Those are not the same. When you look at the graph that is presented to you, the maximum on the left and the maximum on the right are not the same. You see that the one on the right is higher, right, on the y value than the one on the left. So this one we call absolute max, and the one on the left will be called relative max. And the reason why it's called relative max is because there is a higher value, higher y value, so that one obviously is going to take the absolute title, and then this one is the lower one, so it will be called relative or local. Word local makes a lot of sense because it is a maximum locally, right, in its own neighborhood. What kind of a minimum do we have? So some of you say relative, some of you say absolute. You have to just pick one and tell me why do you believe so?
Absolute, because it's the only one there.
Absolute because it's the only one there. Yes?
The absolute would be negative infinity, right?
Well, infinity is not a point, so we can't claim absolute on infinity ever.
Because the relative max is right there.
Nope.
That's why it's relative.
It is relative or local. There are lower y values to the left and to the right. So we do not have absolute min in this case. We only have a relative min. In this particular drawing. When you draw x squared, that one has absolute. So this is x squared, and you have ABS min. If you draw x cubed like this, and this is not x cubed, this is x cubed minus x cubed minus x, let's say. If you draw that, then you have ABS, no, lies, relative max and relative min. Again, the reason why is you have lower points than the minimum, so it can't be absolute because it's not absolutely lowest y of all y's in a domain. Since there is a lower y, right, then that's that. And then we're going to have a sine wave or a cosine wave with all of these on the same height. Infinitely many of them, and each one of those will be absolute max. Maybe I should do this in a different color. So again, all of these are absolutely highest points that you can get, and then you would have ABS min, absolute minimum, because again, this is going to be a wave, and you will never produce a lower minimum of any kind. So these are our this is our understanding of relative versus absolute min and max. The next sentence is very important. Min max occur at what we call critical points. And now we are going to have a definition of a critical point, because when you start solving your problems, you will first find the critical point, and then you will decide whether that critical point is the min max or something that is called inflection point that we are going to see a little bit later in the, it's next class we're going to see inflection points, so we'll know what that means. All right, so let's do the definition. An interior point of the domain of f of x, right? So interior point of the domain, that means if you have a domain that goes from negative infinity to positive infinity, or you have the domain that it's, I don't know, like 0 to infinity for square root, or including for square root and not including for ln. So if you have an interior point in a domain, So interior point is called a critical point of f of x if, number one, oh, you know what I forgot, guys? I forgot to give that name, that point a name. So over here, we need to insert c, lowercase c. That's the name for the point, because now I have to write f prime of c equals 0, which means that the derivative is equal to 0. Or, number 2, f prime of c does not exist. So that's the definition for critical point. And what it does is it tells us the location where min-max, or what we know as inflection point, might occur. Now, to check this, so just to clarify, so you will solve the equation to find c. So here's the example. If f of x is equal to x squared, you all know where the point is, right? You all know what it is, you know where it is, but now we're going to calculate. So the first thing we do is we find the derivative, which is 2x. Then we set f prime of x equal to 0, which means 2x equal to 0. What happened? We set 2x equal to 0. There we go. And when you solve that equation, divide both sides by 2, you get x equals 0. This thing is critical number. Not a critical point, because point is x comma y, right? It's a critical number. And now we go and we find the y value for it, which is, in this case, f of 0, which would be 0 squared, which is 0. And now I have 0, 0, which is critical number. Point. Because I have both coordinates. And we know, because we know what x squared looks like, we know that this particular point is a minimum, absolute minimum. So ABS min. Now we are going to discover, as we go through, we are going to discover methods for more complicated functions, how you can tell what's min, what's max. Right now, we don't have any of those tools, so we will either go back to our common sense, or we are going to actually compute the points and check whether something is min or a max. So we can say f of x equals cosine x on 0 to, let's say, pi over, I'm going to leave this for the second part. Let's not worry about the cosine yet. Let's go and deal with other functions. So we had the x squared. Let's talk about e to the x. What do we know about e to the x from pre-calculus regarding min and max? If you look at e to the x, what do we know about min and max? It doesn't have one. We can't claim max at infinity. Infinity is not a point. Max and min can only happen at the point. So it doesn't have one if you look at it. And we can prove that now simply by finding the derivative, which is e to the x. When you set it equal to 0, this equation has no solution. When it has no solution, that means no critical point, and no critical point means no min max. See? E to the x equals 0 is an equation that has no solution, and the reason is, right, 0 is y equals 0, which is x-axis, and e to the x is above it, so they never intersect, and because they never intersect, they have no solution. And since they have no solution, then there is no critical point. Since there is no critical point, there is no min max, and we are done. Another one of those would be f of x equals 1 over x. If you find the derivative, again, we just know these. We know these graphs. So it's like cheating. We already know the solution. We know there's no min and max on 1 over x. But if you want to prove that there is no min max, you will just go and say f prime of x is equal to negative 1 over x squared. When you set that equal to 0 and cross multiply, you get negative 1 equal to 0. Well, that's not true. So again, no critical point, and all of that means no min max. So these are the calculations. Now obviously we're going to make this more interesting with functions that are not just basic functions like we had so far, but that boils down to your ability to solve equations. Doesn't, right, and take derivatives. The concept is always the same. Now, before we go to those, I want to briefly talk about this point number 2 over here, where the derivative does not exist. You also have to consider that. Derivative does not exist, because you could have a min and max at places where they don't exist. And the example for something like that would be f of x equal absolute value of x. You can clearly see the minimum. You can clearly see the minimum here. And where does it happen? Well, it happens where the derivative doesn't exist. So if you studied absolute values, you know that absolute value is defined as the piecewise function for x, for all x's bigger or equal than 0, and for all x's here that are smaller than 0. And in this case, f prime of x would also be a piecewise function where you take the derivatives of each piece independently. So you have 1 for all x's bigger or equal than 0, and negative 1 for all x's smaller than 0. And if you consider the derivative graph, which I'm going to draw in red over here, so this is going to be y prime, you will have negative 1 from this side and positive 1 on that side. You see that there is no derivative so I'll put it like this. Derivative dne at x equals 0. And that is another location that could produce, not will, but could produce min and max, because you see the example up there we have a minimum. Now, the derivative also doesn't exist when you have a vertical asymptote, which was the previous example with 1 over x. So the derivative doesn't exist at the vertical asymptote, but we didn't have min and max there. So that one is tricky, right? You will have to be able to figure out, right, if it's a vertical asymptote, you have a limit for that. And if it's not a vertical asymptote, then there is no derivative, then it is a point, in which case you claim min or max. So a whole bunch of stuff kind of collides into one concept here. But the most important part is your ability to take the derivative, set it equal to 0, and get the points out. So let's take a look at some of the examples that they want you to enjoy. So find min max for, so let's go simple first, obviously. F of x equals x cubed over 3 minus 9x. So you should be able to differentiate this, set it equal to 0, and calculate values. Go. Okay, let's solve this one. So the derivative is the first thing we find. That will be 1/3 times 3. That cancels, so we just have x squared minus 9. When we set this equal to 0, we will have, we can solve it as x squared equals to 9, x equals plus minus 3. We have two values to worry about. And since we have two values to worry about, we have to calculate y values for each one of them. So when x is equal to negative 3, we have the y value to be f of negative 3. And that's going to be negative 3 cubed over 3 minus 9 times negative 3. This is negative 27 divided by 3, right? It's going to be negative 9 plus 27 to give us 18. And then x equals positive 3. Y would be f of 3, which would give us 3 cubed over 3 minus 9 times 3. That would be now positive 9 minus 27, give us negative 18. So my critical points are negative 3, 18 and 3, negative 18. Now, again, because I know pre-calculus 1 and I know graphing polynomials, at least sketching the polynomials, this is a cubic graph. Cube graphs either look like this or they look like that if you have a to be bigger than 0. Well, since we have min and max, it's definitely the second one. So it will look like this. Oops, terrible. It's too deep. There we go. And this value here is the 3, negative 3, 18. And this value here is positive 3, negative 18. So we see that this one is a min and this one is a max. Now I have to make sure that you understand that you don't have to have positive number to be a max and a negative number to be the minimum, because some of the problems that we are going to run into eventually, so let me write this in blood over here. Larger y value is not always the max. Okay, that's very important, and here is why. If this is going to be, guys, this is one of the standard problems showed up on exams many times. So if you have, let's say, a vertical asymptote like this and what we call a slant asymptote, which you are familiar with like that, and you draw a function that follows these. Do you see how this is a max, right? But its y value is smaller than the min. See that? The minimum has a larger y value. Do we all see that? So you have to be careful. You can't just go blindly and say, oh, this is bigger number, so it's a max. No. There's the example that immediately buries that kind of thinking. So please make sure that you are reasoning with these things or computing the nearby points to see from those points whether the y value rises or falls to create the min or max. Now, again, what I said, these first couple of examples, right, and problems are not as involved as later when we actually get the tools to check whether it's a min or a max. So let me give you another one of these to enjoy. And then we'll do the other part, which will have some of your favorite trig. So f of x equals 1 over x plus ln x. So have fun with that. No pressure, you have 18 seconds. I'll be right back. You all got 7? Good, because that would be wrong. All right, let's go. So we have the derivative. First off, we see vertical asymptote at x equals 0. And since it's a vertical asymptote, if we get any part of calculation to give us 0, we know we have to throw it in the garbage, right? Because 1 over x has a vertical asymptote at 0, ln x has a vertical asymptote at 0. The domain of this thing will only be 0 to infinity, because ln x doesn't have anything to the left. So, that kind of analysis in the beginning helps a lot with these solutions. It's all pre-calc talk. So now the derivative is negative 1 over x squared plus 1 over x. And we are supposed to set this equal to 0. Now, to solve this problem, you have options in life. And one of those options is to, rather than look for common denominator and stress with that stuff, when you have two fractions like this, you can just move the negative one to the other side and then cross multiply. Right? So it will be faster if we just write 1 over x is equal to 1 over x squared. And when you cross multiply, you get x squared equals to x. And now, x squared minus x is equal to 0. And you have x minus 1. X equals 0, x equals 1. And we know we need to throw this one in the garbage because vertical asymptote, right? And we have our critical number over here. Critical number. And what I do with the critical number is I bring this value back into my original to find y. So y, f of 1, would be 1 over 1 plus ln of 1, which is 1 plus 0, which is 1. And I finally have my critical point, and it's 1, 1. Now the question is this a minimum or a maximum? Or neither? Because it could be that inflection point that we didn't cover yet. So now you're asking yourselves, well, what is this? Now these are graphs that you know one by one, but when you add them together, do you really know what the resulting graph looks like, right? So what we should do is we can calculate the y value of the points that are relatively close to this point, and those y values will be either higher or lower than the y value, which is 1, and then we'll know what 1, 1 is. Let me just tell you what I mean, and then we'll do it. So if I have a minimum, right, which is at, let's say, x equals 1. If I compute x equals a half, and x equals 3/2, you see that it will produce y values that are bigger. If these y values are bigger than the y value for the middle point, then the middle point is a minimum, because those two that we calculate are larger. Same thing goes this way. If you have a max and you compute 2 points on a side, right, this is your x equals 1, and let's say this is 1/2 and this is 3/2, which is the numbers that we are going to use now, you see that these two y values are lower, right? These values are lower than the top, and that also, right, deals with. So as you can see, there is an annoying way for us to tell this. This will be much easier later on when we find the actual nice, simple way to tell whether something is a min or a max. Right now, we are in the annoyance mode. So we have test points. X equals 1/2. So the y value for that would be f of 1/2, which is 1 divided by 1/2 plus ln of 1/2. And this is going to be 2 minus, and the ln of 1/2, we'll just use the abacus for ln of 1/2. So that's going to be about 0.7. It's 6931, but 0.7. So this is about 1.3. 1.3 is bigger than 1. All right, so we are already looking into a minimum. X equals 3/2. So y equals f of 3/2. We have 1 divided by 3/2 plus ln of 3/2. Now ln of 3/2 is not going to be a positive number because 3/2 is bigger than 1. So we have 2/3 plus ln of 3/2. So ln of 1.5, and that's going to be 0.4. And 0.4 plus 2/3. If you 2/3 is 0.6666, right? So this is also going to be bigger than 1. So both of these values that we found are bigger than 1, and 1 is in between. So this is the point at x equals 1/2. This is the point at 1, and this is point at 3/2. So we clearly see it's a minimum. So that's how I know that 1, 1 is a minimum, by computing the 2 points, one to the left, one to the right. Again, very simple, but annoying because you have to compute these things now. Later on, you will actually get what min and max are for free. You will be calculating something else, and along the way, it will just, tell you, oh, by the way, your critical point is a min, or oh, by the way, your critical point is a max. So just give me 2 sections, all right? We're going to do that in 4.3, which is next class. So this is just 2 days of annoyance with this. All right, so now we know how to deal with min and max, critical points, and so on. One more thing left in this section, and that is when we have intervals, right? The closed interval for the function. So we chop up the function, and for those, we are guaranteed to have a min or a max. So say that you have a sine function. We already said that, but here is a sine function, right? It's going to go forever, and we said it has infinitely many absolute max values and infinitely many minimum values. Now, what we like to do with sines and cosines and all of these trig functions is to reduce them to their principal domain, which is just the one oscillation, right? So our sine would be from 0 to 2 pi, and it would have exactly 1 max and exactly 1 min. Now, this repeats infinitely many times, but once this is on domain negative infinity to positive infinity, this is on a domain 0 to 2 pi. So now, we can take functions that do not have min and max, and by chopping their domains, create min and max. So an example of that would be f of x equals 1 over x. What we know is that the graph looks like this, and it has no min max. And we're done, right? But then, if you go and say f of x equals 1 over x on 1 to 3, now the situation is completely different. You are throwing away the rest of the function in the garbage, and you are only keeping 1 to 3 piece. So now if I am to graph this function, I will have something like that. And that clearly has an ABS max and the ABS min, and it happens at these endpoints. It's not guaranteed to happen at endpoints, but in this case it does. So I took something that had no min and max on a global domain, right? And the global domain is from negative infinity to positive infinity. And once I restricted that domain, right, cut out a piece, it became this, what I have over there. So now I have this. And the way to compute would just be to actually plug the endpoints of the interval into the original function to come up with y values. So in this case, we have we have a max, well, ABS, right, because we know it's absolute max at 1, 1, and ABS min at 3 and 1/3. It's not a root, it's right. So this is what we have for this example. Now, as I mentioned, and I'll write it in blood, ABS max min do not have to be at endpoints. They do not have to be at endpoints. And here is an example. If I take f of x as x squared and put that on -2 to 6 domain, it would graph like this, right? Because this is where the, oops, go away. I mean, not you, the line. It was perfectly timed, right? as you're walking back in a classroom. Go away. So if this is my -2 and this is my +6, right? So what do we have? We have ABS max at the endpoint. We have relative max at the endpoint, but your ABS min is not at the endpoint. You can have any combination. So with this new knowledge now, you know that you can look for min and max on the inside of the interval using the derivative procedure. And then when you find all of those min-max values, you also compute endpoints in addition. So the highest value in that case is going to be your absolute max and so on. So now, for this example, let's say number 1. We use f prime of x equals 0 to get all min-max inside the interval. And that is where we found ABS min to be at 0, 0. So this is the procedure we already did. If I go back, right, to our first example of today, there it is. That's where we found it, right? So you still have to do this particular example to find all of the min and max, and that goes for every function we covered, right? Even if it's on the restricted domain. So that's the first part. And then part 2 of the problem is y equals f of -2, which is -2 squared, which is 4. So we're going to have -2, 4 as a relative max, and y of f of 6, which is 6 squared, which is 36, which is 636, which was the ABS max. And now it all matches. So you have the full problem, except the part 1 was done earlier, so I didn't do it. But all of the problems that are on the finite domain, where the domain is chopped up, you will have to use what you know, right, in the middle to find the values, and then use the endpoints and find the y values for that, because those could be min and max. Now, I just need to point something out, because it might not be clicking right now, but maybe when you start doing the homework, the question might appear. And that is, any time when you have the restricted domain, you are guaranteed to have min and max. But then many students along the way said, well, hold on, if I just use a line segment like this, then what does this mean? Because you said that every function must have absolute min, absolute max if it's on the restricted domain, and this is restricted domain. Let's say this sits here in the xy plane, right? And this line over here is y equals to 2. So y equals to 2 on negative 3 to 4. So this is perfectly defined function, right? So you might say, well, hold on, this doesn't fit your definition that every function, right? But see, the trick with this function is that it's a constant, right? So do you expect to have a min and max on something that is constant? No, right? In order for something to be a maximum, it has to have lower points somewhere, and something to be minimum has to have higher points somewhere, right? So the question doesn't make sense. And you have those questions that make no sense, like what's south of South Pole, and what's north of North Pole, and what was before the Big Bang. Like none of these questions make sense to even be asked, right? So the same thing over here, right? It doesn't even make sense to ask a question on, well, what is absolute max and what is absolute min? In this case, it's a constant function. So no max, no min function is constant. No min, max, this function is constant. This is terrible. Constant. There we go. Boom. The last question is the one with the cosine that I wanted to ask earlier. So f of x is equal to cosine 3x on, and let's pick the domain, let's say from negative pi over 12 to pi over 3. So try this for about 120 seconds. Okay, let's take a look. Derivative of cosine is negative 3 sine 3x, right? And we set that equal to 0. Now, sine 3x, well, negative 3 when you divide both sides is just going to cancel. So now, when is sine 3x 0? Sine is 0 at 0, pi, and 2 pi. So, since sine x equals 0 at x equals 0, pi, and 2 pi, we have 3x equals 0, 3x equals pi, and 3x equals 2 pi. Now this one is x equals 0. This one is x equals pi over 3. And this one is x equals 2 pi over 3. Now, I'm going to kill this one because it's outside of negative pi over 12 pi over 3. So that one is kicked out. So I only have these two, x equals 0 and x equals pi over 3. Now, as you can see, pi over 3 and pi over 3, they collide as the same point. That's fine. So now what I'm going to do? Well, I'm going to find the y values. So y equals cosine of 3 times 0 is cosine of 0, which is 1. So I have my first point at 0, 1. And y equals cosine of 3 times pi over 3, which is cosine of pi, which is negative 1. So I have pi over 3 comma negative 1. And I know that I also have to test the endpoints. Let me say here endpoints. So y of this is going to be f of pi over 12, which is cosine of 3 times pi over 12, which is cosine of pi over 4, which is a root 2 over 2. That gives me the point negative pi over 12, and this is negative pi over 12. I didn't put the negative because cosine is even function, so when you plug in a negative value, it just disappears. You can drag this negative if you want to, it's just gonna go away. Root 2 over 2, and y equals f of pi over 3. We already have that, so I'll put 3 dots, equals to negative 1. So this is pi over 3 and negative 1. So now, since there are no interruptions in the domain or anything like that, we know that we have the ABS max at 0, 1 and ABS min at pi over 3 negative 1. So that will be the full problem where you use the first part of the lecture to take care of the function in between the endpoints, and then you just compute y values for endpoints, and you see what has which one is the max, which one is the min, and all of that good stuff. So that's 4.1. Simply put, your job is to locate minimum and maximum of the function, and we are going to see throughout the course, right throughout chapter 4, that is what we need, not just for graphing, but also for word problems, because we want to know maximum profit, minimum cost, maximum distance, and minimum surface area, maximum volume, and a whole bunch of other stuff. So this is going to be very useful to us. All right, that's it.